SAY Labs, which is behind engineering for SAY. My background is in Web3. In 2017, I was a co-founder of a little voting startup during the ICO days. Then I joined Open Zeppelin for a couple of years, and then after that I was leading technology for Forta, and as of last October I joined Core Dev for SAY, and I'm pretty excited about working on an L1. Here we go. All right, so just a brief introduction to SAY. So right now we're the fastest L1 in existence with 390 millisecond block times. We've been in mainnet since August 2023. Today in mainnet it supports WASM contracts, so you can build in a number of different languages, but it's like a COSM WASM kind of experience, and it's very fast. So you click submit, you click confirm, and it instantly mines. So from a user's perspective, they can actually be a little bit surprised when they're using it because it's particularly fast and they're used to seeing loading bars and things. So it's been a lot of fun to work on. So the biggest feedback we received was from developers, hey, do you have the EVM? Can I build with my stuff I know? Can I use Hardhat or Foundry? How do I move my stuff that I've already built and already audited onto another chain? So we said, okay, let's add the EVM. And we didn't just add the EVM, we added the first parallelized EVM, and it's now the fastest EVM L1. So SAY V2, you might hear this in our blog posts, you might see it on our website. It's an upgrade to the existing network. It's not a new network, it's not a separate chain, it's not a new token. It's the same thing that we have today, except it has all these new toys. So the first thing it can do is it can do EVM compatibility. It runs parallelized execution without you having to do anything. So you just send transactions like you normally do. You don't have to tell us what your dependencies and state accesses are, and we'll parallelize them for you. It also adds a new state storage capability called SayDB, which pushes a lot of the activity on runtime in memory, but also makes it possible to control state float. And I'll talk a little bit about these in just a second. But the big takeaway is that we have a public DevNet right now. You can go play with it right away. Just go to say.io, and we'll give you the RPCs as a faucet, and you can start building EVM. Mainnet is coming very soon, like a matter of weeks. So we're just getting through audits, making a couple performance tunings, but it's pretty much go complete for mainnet. All right, so why EVM? Well, 87% of crypto developers work on the EVM. So there's a lot of Web3 native developers out there that only know Solidity. This is a huge hurdle if you're trying to ask somebody, hey, move on to my chain and learn a new language, please. You know, and it's just a hard problem space. So they've already learned the idiosyncratic behaviors on the blockchain. They understand temporal code. They understand blocks. They understand reentrancy attacks. They've seen a bunch of hacks happen. They have auditing relationships. They're not ready to just shift over and just shift, you know, onto a new chain. So this is really going to help out SAY because we have a lot of developers ready to build, and we also have a fast chain for them. Yeah, let's see here. Okay, so why have another L1? Like why have yet another place where you can send transactions just like all the other EVMs? Like why do this? Well, Ethereum's very slow. Even if you're building an L2 on top of Ethereum, it's incredibly slow. So like you can only get, let's say, dozens of transactions per second, even if you're an L2 on top of the L1. This also leads to a lot of anti-patterns in terms of how you're designing your application, because you're having to work around these speed bumps along the user journey and around the possibility of reorgs, and you have layers, and you end up building and compounding your risk as a result. So this is why we think there should be fast L1s in the space. So that's what SAY is focused on, is being the fastest L1. And we know there's a lot of other kinds of approaches to this, but our opinion is that we want to make better user experiences for users, and that's why we're focused on speed. All right, so the SAY V2 EVM is 100% bytecode compatible. You don't have to change any code. It supports all the JSON RPC endpoints. It's very cheap gas. I took a little screenshot of our DevNet here just to kind of show you kind of the aspect of how cheap this can be. And this is me sending myself some say, which is our native token. You can see it's like 0.000, sorry, 4 zeros and then a 3, and say is something like 80 cents right now. So you can see just that's particularly cheap. It's almost essentially free. It's also very, very, very fast. So I say no code changes needed. One thing you need to be aware of if you're moving a Solidity contract onto say is that if you have assumptions about the block times inside your contract, like to calculate some sort of staking yield over time, you might need to update that because we have a lot faster block times. So you don't want everybody to instantly vest their funds or something. But structurally in bytecode, it's compatible. All right, so you might be wondering, well, how does say go fast? Like what does fast mean? How does that work? So these are the speed enhancers, and we're just sharing all of our information. We have nothing patented. There's all open source. You can go to our website and go to our GitHubs and just dig through it yourself if you like. But one thing we do is we parallelize transactions on the EVM. This is coming with the say v2. We also push as much state access into memory as possible. So we think we can essentially avoid state access for almost 95% of the transactions, and then make it very quick to access the state in other cases. We also had to control for state bloat, because if you're sending, let's say, 10,000 transactions per second, state bloat becomes an instant problem, because you have to keep up with all these transactions and logs and side effects and state root information, and state bloat had to be rethought in order to achieve what we were trying to do. Lastly, we have twin turbo consensus. This is already out there today in V1. I just wanted to talk a little bit about it because it really speeds up the block times. All right, so what is parallelization? It's when you run everything at the same time. It's when you run, so I have a little picture here. I did not draw this, ChatGPT produced this, but you can see all these little frogs driving their cars to the toll booths. The more toll booths you have open, the more car throughput you can get. It's a very simple concept. Instead of running one after another, run them at the same time. This also helps to take advantage of modern hardware, which are almost always multi-core now. So as we get more improvements on hardware, we'll be able to get more throughput on the say chain. All right, so we have a breed of parallelization called optimistic parallelization. There's a couple different ways you can go about parallelization. One is like more of a dependency assertion type. This is more like a Solana or what we had in V1, where a developer could actually say, I'm accessing state A, B, C, and then as part of that definition, the chain can figure out what the dependencies are. In our case, we found that to be very onerous on the part of the developer, because how do they know exactly what's going to happen with all the composability that should happen across these different contracts? So what we do is we would just try to run them optimistically at the same time. Let's say you're running these 3 transactions and you find a conflict. We'll detect that conflict, bail on the transaction, and rerun the one that needs to be rerun. There is a lot of literature on this problem space, and there's a lot of details here, but just so you know, we run them all at the same time, we detect conflicts, we resolve conflicts for you, and then continue through. The worst case is a little slower, but the best case is a lot faster, so this is sort of a trade-off to make. One thing we're exploring in the future is impacting gas a bit by how parallelizable your transaction is, to try to incentivize some of the behaviors around design patterns that lead to better parallelization. Right, so what happens when you run 10,000 transactions per second? You end up accumulating tons of state. And this is what ChatGPT gave me for state bloat. It's a giant balloon overtaking what looks like possibly Manhattan. This is not actually an actual size of state bloat. Depends on the size of your server. So state bloat can consist of account balances, smart contract state, the tree structure of your state root, and everything that leads up to that root. And it impacts a number of things. One is, like in our production right now, it's about 16 terabytes to hold an archive node. This is before the new update. And it's also, it impacts sync time. So if I add a validator, I don't want to wait 6 months for it to sync from the beginning. And that kind of thing can really impact your network long term. So this is our SABB architecture. This is part of SABB2, and this is going out. It's in DevNet right now, and then this will hit Maidment in a couple weeks. So you can think of this like two layers. One layer is the state commitment layer. This is where we maintain an in-memory tree. You'll notice there's two different colors here. It might be kind of hard to see for some, but you have in-memory nodes, and then you have what we call persistent nodes. These are lazy loaded into memory when they're accessed, and then they kind of stay in memory until the next snapshot time. So periodically, these get flushed to 3 files that consist of the key values, the leaves of the tree, and the nodes of the tree. And these can happen in parallel. While a set of blocks are going, you'll have an active tree. And meanwhile, you'll end up with a like a blue-green tree. The second tree is being populated while the first tree is being flushed, and then the second tree is moved on to after that snapshot is taken. So this allows basically no disk access for most transactions. How do things actually make it to disk? Well, asynchronously, we have a write-ahead log that's constantly being streamed to. So you'll notice, like, if you have a background in databases, this is kind of a common shape where you separate the problem space of what's in memory, what's a write-ahead log, and then how does it get to disk. So something like Postgres, for instance, might be structured more like this. All right, so this gave a lot of improvements. So that 16 terabytes that we have right now in production was reduced by 60% on this new shape. So it was able to drop a lot of storage. On disk is, we don't actually keep the tree structure, we just keep the key values. And then when it's rendered into memory, the tree structure emerges. So that's why we're able to shut down. All right, lastly, twin turbo consensus. This is a big part of our speed. I'm just showing you here, this is before twin turbo consensus. There's this moment where everyone had to stop and ask, are we agreeing with each other? We're able to optimistically vote on a block before we actually finalize here, and only in the case where something really disagrees does it fall back to the original model. But optimistically, we're able to shut it from about a sub-second to 390 milliseconds as a result. Okay, so just the big takeaway. Before, we had WASM, we had access-based parallelization, and then regular state storage. Now we have EVM, optimistic parallelization, and more of an optimized state storage. Right, and if you'd like to play with it, especially if you're writing a kind of a user-facing app that needs to be quick, try our DevNet, try it out. I'd love to kind of hear what you think, and if you hit any issues with it, of course, reach out. I think that's it. Thank you.